Welcome to my projectbazaar.com. Let us discuss about the outage constraint sensing threshold design for decentralized decision making in cognitive radio networks. Let us discuss about the abstract of the product. So efficiency in spectrum utility has been concerned in wireless communication for a long time. So cognitive radios have been seen as a solution to occupy the gaps in the licensed spectrum through spectrum access and simultaneous spectrum sharing techniques. So for this, proposed spectrum sensing has been involved to providing the accurate statistical information regarding license for primary user activity in its spectrum. So in this proposed work, we design a new sensing thresholds that take into account the outage cost to the primary user as a consequence of cognitive or secondary users accessing or sharing the set spectrum. With this a new threshold, we can see more protection to the primary user and secondary user, spectrum access transmission based on the misdetection, and eliminate the most common assumption made with spectrum sharing systems. Our threshold also work with a dynamic decision making algorithm that allows the secondary user to use only the statistical sensing information to understand the network dynamics and determine its transmission opportunities and corresponding power consumption. So in a decentralized and uncooperative cross-area network, so finally we calculating the spectrum sensing, spectrum access, and also sharing the spectrum by using a threshold design, and finally calculating the energy reduction and decentralize of the area network. Let us discuss about the flow diagram of the product. So this is the overall flow diagram. First of all, the system model. In the system model, we presenting for the primary user and also a secondary user, and then convex restriction formula. So in this paper, consider outage-based precoder optimization. Specifically, the scenario of the interest is multi-user MISO downlink, and then Gaussian CSIR. So that is a channel state information error model is adapted. So we focus on the outage constraint problem. So that is a convex restriction formula. So and then the goal is optimize user signal convergence matrix for total transmission power, minimization while satisfying the achievable rate, and then outage constraint. So that is the optimal transfer scheme, and then it's a spear bounding. So we developed two novel convex restriction. So one is the methods for aforementioned rate outage constraint problem using probabilistic technique. We show that these methods together, traditional robots optimization convex restriction method, can be viewed as implementing different traceable analytical upper bounds, and then also calculating the Gaussian quadratic form. So that is a probability constraint, and then Bernstein type of inequality. So finally we calculate the decomposition of the process. So that is a semi-defined program. So already it's defined by the convex restriction formula. So all three methods involve convex. So that is in the spear bounding, Bernstein type inequality, and then semi-defined program. So these are all the already converted to the program of to find the outage probability of the error. So finally we analyze the performance complexity trade-off of the three presented convex restriction method. So the complexity orders of the three methods when they implemented, so IPN are shown. We then we analyze the relative tightness of these methods. It should be emphasized that the tightness analysis in particular non-retrieval from a theoretical viewpoint. So the insights obtained from our analysis are in the agreement with the simulation results. So these are the performance analysis of the process, and then we calculating the organization and notation. So the rest of the include the system model and the problem statement, so are given in the paper. So three convex restriction methods are presented, and then complexity and comparative approximation performance of these three methods are analysis in the performance. Finally we get the performance analysis. Simulation results are provided by using the decomposition, probabilistic constraint, optimal transceiver scheme, and also a convex restriction formula. So these three methods useful for calculating the transpose and Hermitian transpose respectively. So finally we calculated this pair bounding, Bernstein type of inequality, and then semi-defined program. So these are the overall flow diagram of the process. Let us discuss about the running procedure for the product. So click the main file and then run. So there are outputs are displayed. So these are the outputs related to our flow diagram. First of all, we generating the input signal. So input signal we consider as a randomly, and then 1, 2, 3, 4, 5, and so up to 5 signals are generated. By using the input signal, we calculating the outage probability of the results, and then these are the channel coefficients. So first of all, finding the input and then finding the channel coefficient of the result. So already we know that the process of calculating the channel coefficient by using the sphere bounding and then f int case int. So these are the calculating of channel coefficient of the process, and then this is the receive signal. So receive signal first of all we getting the input signal and then channel coefficient, and then we calculating the receive signal of the process. So by using all this process, first of all input signal and the channel coefficient and then received signal, and then calculating the achievable rate of the process. So calculating the achievable rate up to the input signal to the calculating the boundary box and then optimizing value of the process. The three methods, so that is a convex restriction problem by calculating the achievable rate of the process. In this figure show the feasibility performance of various methods. So this is a feasible rate in the percentage, and then so this is a comma in dB. So these are the method 1 and method 2 and method 3, and then finally probability of SOCP. So these are the different types of feasibility performance in various method compared to the existing and proposed method. So these are the feasible rate that is calculating in the gamma. So that is calculating the percentage, and finally that is calculating in the gamma in dB. In this figure, that is x-axis provide a gamma in dB, and then y-axis average transmission power of dB, and then transmit performance of power performance of various methods of the method 1 and 2, and finally calculating the probabilistic of SOCP. So this is the transmitted power performance. So how to the power average transmission power by using the calculating of dB, probabilistic of SOCP. So this is also a transmitter power performance of various method and average transmission of in dB and gamma also in dB. So while calculating the outage probability, how much outage probability will the decision making algorithm is performed, and calculating the transfer power with various power of incidence. So these are the overall running procedure for the. Thank you for listening this video.